So we have seen that if there is a set of numbers in BST, the first number that I encounter, that is considered as the root of the of the BST, and the others numbers will be inserted according to the rule of the BST. We'll start checking every time from the root, and maybe depends on the value, key value that I want to insert in the tree. I will either go in the left or right, and ultimately I will the key value will get inserted as a leaf node. So just as an example, if I consider there is some arbitrary value, say 10, 15, 5, 3, 12, or maybe 14, something like this, and as an example, this is obviously will be my root, right? Will be my root, and then 15 will come, and we see 15 is greater than 10, so 15 is inserted here. You see right now 15 is the leaf node, right? 10 is not leaf node, it is root. And then 5, and you see 5 is also lesser than 10, so lesser than 10, this is blank, this part is not busy, so I will keep 5 in this side. So now my total number of leaf nodes become 2, and then 3. So 3, where 3 will come, 3 is lesser than 10, so it should come here, and with 5 I will check 3 is also lesser than 5, so it will come in the left of 5 again, right? So now 5 is not become any leaf node. Instead of 5, now new leaf node become 3, and then similarly 12, so I will put 12 somewhere, something like this in this side, right? And then 14 will be somewhere in this side, which is lesser than 15 but greater than 12. So one thing is clear from this example, that is whatever key value I insert in the BST, doesn't matter, any key value is always inserted as a leaf node. You cannot insert something between 5 and 10. Like in case of a linked list, we have seen that we have a set of numbers, say 10 numbers stored in a 10 different nodes in a linked list, and I can insert a value in between 5th and 6th node easily. I can insert that, right? But you cannot do this one in case of tree. You cannot say that something lesser than 10 and greater than 5, 6, greater than 5. So for example, 7 come. You can say that if I put 10, then 5, 10, then 7, then 5, then it is okay. Yes, it is true. Initially it was 10, 5, and I inserted 7 in between 10 and 5. So it is not violating the rule of binary search tree, but you cannot do this. By the rule of insertion, if your data is 10 and 5, and if you encounter 7, with this existing, you cannot change this existing BST. You have to insert 7 somewhere as a leaf node. I mean, obviously lesser than 10, 7 is lesser than 10, so it will come here, and with respect to this, 7 should be inserted somewhere here. So that means always data is inserted as a leaf node in case of BST. Now, in case of insertion, that is okay. But what about in case of deletion? You cannot say every time that we will start deleting the nodes from the leaf node. You cannot say that. So as a programmer, if you have already created a BST and there is a key value someone given to you, and if someone asks you that please delete this particular value from this tree, that means there is no guarantee that that value will be the leaf node. That value may be maybe the leaf node, or maybe non-leaf node, even maybe root node also. So how we can handle in this situation, this particular situation for deletion? Let's try to realize it. So let's do it. Before we go through the deletion process, we have to understand one thing. We have to remember one thing we have done in the previous class, maybe, that is the concept of in order successor. What is in-order successor? If I have a BST and I sort the numbers or the key values with respect to in-order sorting, in-order traversal, then in-order successor of a particular key value is the value which comes after the value in the in-order traversal. So that means if I do a in-order traversal of this particular tree, it's very trivial. I can easily say it's nothing but in increasing order, right? We know that. So your in-order traversal data will be something like 3, then 5, then 10, then 12, then 14, then 15. So if you do an in-order traversal of this tree, your data will look something like this. The traversal order will be something like this. And according to the definition of in-order successor, say for example, what is the in-order successor for this 10? In-order successor of 10 is 12. In-order successor of 12 is 14. In-order successor of 3 is 5, something like this. So here one thing is clear, there is no in-order successor in the extreme right node of a BST which does not have any right child. You see, which does not have any right child. Why I am saying? Because if I consider this one, in-order successor of 15 is what? There is nothing. Why? Because 15 doesn't have any right child. Because 15 was in the extreme right which doesn't have any right child. If 15 has a right child, for example 18, then naturally this 18 will come here and there will be some in-order successor. But 18 will not have any in-order successor because 18 is the extreme right which does not have any right child. Similarly, we have one more terminology, that is in-order predecessor. So in-order predecessor say just opposite thing, that if I just sort the key values with respect to in-order traversal, the value that comes before a particular value is considered as an in-order predecessor of the value. So in an opposite way, you can say that 15 is in-order predecessor of 18, 14 is in-order predecessor of 15, 3 is in-order predecessor of 5. Similarly, you see 3 doesn't have any in-order predecessor, nobody has, because 3 was in the extreme left, which does not have any left child, just the opposite mirror image you can consider. So this concept of in-order successor will be important in case of deletion. How? Let's see it. So let's take a situation where I have a tree something like say 10, then I have in this side 5, in this side I have 15, then 12, then 14 suppose, and in this side suppose 13. So a very long deep tree, and in this side suppose we have 19 or maybe 20, suppose 20, then say in this side I have 17, and then I have say 16, and in this side suppose I have 2, and then in this side suppose I have 4. So lot of nodes contain only one children. It may happen, it's a correct BST, there is no problem in this case. So now suppose this node you have, this BST you have created, and now we have to delete something. Now see, in this particular situation there are 3 possibilities. If I want to delete a node, that node may be 4, that node may be 2, maybe 5, maybe 10, maybe 15, any node it's possible to delete. So if I want to delete these nodes, there are 3 possibility can happen. I mean 3 possibility can be there as per the node. What are the cases? The case number 1, you can say that the node is a leaf node. Second point, the node is non-leaf node. Is a non-leaf node. Now, this non-leaf node can have two different cases. One, you can say that the node has say both children. Second point is that you can say that the node has, sorry, here I will have three cases. The node has only right child. And here the third point is that the node has only left child. So other than this, I mean the case number 1 and ABC, I mean ABC under 2, other than these cases there is no possibility, right? So we will start one by one. So we will see first this case, that what will happen, how we can actually delete and keep the other part of the tree remain as it is in case when the node is a leaf node. But remember one thing, I told you already that this particular path is unidirectional. So that means there is no way to go back to the parent if you don't store them before jump to left or right child. I am saying this because I will start journey from here because this is my root and I don't know when I will get that particular number which I want to delete. When I will realize that if I don't have a pointer or something so that I can find it, the parent of that node, I cannot do the deletion procedure perfectly. Why? The reason is that, for example, consider 4. 4 is a leaf node. So if you want to delete 4, since 4 is the leaf node, that means if you delete this part, the right pointer of this node 2 have right now address of 4. And if you delete this node 4, that means 2 should not point anywhere. That means the right pointer of 2 should become null, as we know. So to access the right pointer of the parent of 4, some pointer has to point this node so that I can access. But when I started journey from 10, I can see that this is not 4. So what you will do, you will come here. You will check this node value, key value actually, again. So this is not 4. So again you will come in this side. And now whether you will come in the left or right depends upon the value that you are searching to delete is greater than the value where you are standing or lesser than. So it's very trivial. It's very easy to realize. Now in this here you have checked that it is not, again still it is not 4, but 4 is greater than this value, so you should come in the right side. That's true. And when you will stand here and there, you will realize that yes, right now the node where I am standing, that is actually the node you want to delete. But if you just delete using say somehow, but how you will reflect this deletion with respect to the right pointer of these two? if you don't store the address of 2 in some pointer so that you can access this, right? That means when you will jump from a particular node to its left or right child, you should store the address of that node somehow. Okay, so that means I can simply say I mean, if I just write a pseudo code, what I can say that it may also happen that the node that you want to delete is not even exist. For example, if I want to delete 3, then what will happen? 3 is not there. So after lot of left right, a time will come when the pointer that you are using to point those nodes, actually searching the nodes, will become null. Because if I consider that I want to delete 3 in this particular tree, which is not possible because 3 is lesser than 10, so it will come in this direction, and more than 2, so it will come here, but 3 should be now in the left of 4, right? That's why when you are standing here with some pointer p and you will check that p data is not equal to the search value that you want to delete, then you will check this search value is lesser than p data, so p should come in the left side, but left of this 4 is right now null. So what will happen? P will become null, and if p become null, that means surely the data doesn't exist. That's why I have crossed even the last node, I mean the leaf node. That means, I mean, obviously I will start generally considering p equal to head, I mean sorry, not head actually, technically we say root, and then we can proceed p not equal to null, right? Until p not null, I can start checking, right? So I can say that here, suppose there is a search value s whose value is say 4 right now, I'm saying correctly, that is, this is what I want to delete. So you see, the first thing that you have to do, you have to check if p data equal to s, then fine, then we will start the deletion process. The deletion process will start. But if we see that it is not equal to, then we have to check it. If the search value is greater than p data, that means surely the value that I want to delete is in the right part of the node. So I must change my position from p to p right. So that means this initially it was p, and now this will become p, because suppose I want to delete something, for example, say not 4, for example, say other value. I mean, if I consider it is, I want to delete 13 in that case, just assume. So now you see, if you find after coming here, if you somehow see that whatever you want to delete is this node, then how you can change, I mean how you can delete this? If you don't, you must store the address of this parent, because it will be required in some cases. And that is my point actually. I mean, you must store in some another variable q equal to p, so that when you are jumping to right, you must store the address of its parent to some another variable q. And similar situation in the other case also, that I am writing as else. Else means definitely s is lesser than p data. In that case, definitely I should go like similar thing, q equal to p, but here you should write p equal to p left. And anyway, so that means after some combination of this P equal to P right or P equal to P left, I hope that you will reach to this particular node, this one. And according to this code, if P is pointing this 4, that means Q is pointing its parent. Now you realize that wherever you are standing right now, that is you want to delete. So what to do? I should keep the right pointer of 2 as null, because I want to, if I want to delete this 4, it's a basically leaf node. That is why I can directly delete this 4, as well as I have to connect this, I have to cut this connection. But question is that when they are same, like this situation, it can be true for case 1 and also case 2. Case 2 means A or B or C, that we have just seen in this situation here. So that means as soon as this situation will happen, we have to start checking under which case it's coming, right? So I'm just writing this part here, that I have to check it first. See, the first case is leaf node. How I can check? Both are null, right? So I can check in this way, that if P right equal to null, I'm just writing on, I'm writing equal to only, just I'm writing pseudocode, that's why. And P left equal to null. So if both are null, that means it is under case 1. That means it's a leaf node. That means I have to delete this and cut this connection. Now which connection? We still don't know whether P is left child of Q or right child of Q. P can be left child of Q also. If P is left child of Q, in that case left pointer of Q should become null. If P is right child of Q, then right pointer of Q should become null. So that means here now I must have another checking. That is, if P right, if Q right equal to P. If this Q right is equal to P, it becomes a little bit clumsy. Let's correctly write it. If Q right is equal to P, it means P is basically right child of Q, that we have seen in this case. In that case, what I will do? I will basically cut the connection between Q and P. So I will just write Q right equal to null. Else means Q left is definitely equal to P. If Q left is P, that means whatever I want to delete is nothing but left child of its parent. So in that case, I should cut the connection left point with left pointer of Q. So I will just write Q left equal to null. Now thing is left, that is we have not yet vanished that particular area that is occupied by the node P. So we can easily do that. You know that there is a function free. If you write free P, the node that we had will be vanished. So that means I can say that after this situation happened, something like this has vanished, this connection has cut. So this is a situation. Now before I proceed more, remember one thing, that after deleting a particular node in any binary search tree, the in-order traversal is always maintained, at least with respect to the order of the other data of the BST that is left. What I mean, that if you do the in-order traversal of this tree, what will happen? Just if I write this, I will find, considering 4, if I say it was 2, then 4, then 5, then 10, then 12, 13, 14, 15, then 16, 17, then 20. So if you do the in-order traversal of those binary search tree, you will find this. And always remember, whatever node you delete doesn't matter. After deleting the node, the BST that will left should have the same in-order traversal other than the node you have deleted. For example, after deleting this 4, only this 4 will vanish. But relation among the other numbers should remain same. They should not become haphazard or even a single change. If there is a single change in the in-order traversal order in the newly formed BST after deletion, then you have done something wrong, surely. I mean, after deleting this 4, if you take the in-order traversal of the BST, you will find 2, then 5, then 10, 15, 12, 13, 14, 15, like this. As if only 4 has vanished. Other part, the order of the numbers or the key values must remain same. And this is true for all these cases. So you see, in case of a non-leaf node, the deletion is not so straightforward. For example, let's take a situation. Under case 2, let's take this case A, that is node has both children. That means, for example, 15, or maybe the root itself 10. In these two cases, if I want to delete 10, this 10 has both children, 5 and 15. So naturally question will come, if that root vanishes, then who will come? Who will take over this node? Obviously, it's not possible that you will keep 5 over in this side. Then in that case, if the 5 has some right child, then where this right child of 5 will go? Right? So a chaos situation will arise if you try to do some straightforward, try to apply some straightforward technique. So we will actually not directly delete this particular node in this situation. We will take a different approach, and remembering the point that I just said you, that after deletion of the node or the key value, not at least, I mean, you should not say node, you should say key value. So after deletion of the key value, the in-order traversal should be maintained same as it was for the original tree. Other than only the value that I have deleted, only that will be not there. Other value will be in the same order that was present in the original tree. So that means just assume that this 4 was there, or maybe you cannot even, I mean, newly created, in the newly formed situation, it is something like it become, I mean, just a minute. So newly formed situation is 2, then sorry, yes, 2, then 5, then 10, then 13, sorry, 12, 13, 14, 15, 16, 17, 20. Now you see, if I want to delete 15 from this set, you see 4 is vanished because I have deleted this 4. So if you want to delete 15 from this situation, it should not harm the order of the others number. So that means whatever the tree that will be formed after deleting the node 15 should have a in-order traversal 2, 5, 10, 12, 13, 14, then 16, 17, 20. So in this situation, what we do, since it is not possible to delete 15 right now because it has both child, what we do, we replace actually this 15, this key value 15 with its in-order traverse, in-order successor. Now what is in-order successor of 15? In-order successor of 15 is 16, right? We can see easily. Because after at the in-order traversal 16 come after 15. That means in-order successor of 15 is 16. So the idea is that I will replace 15 key value by its in-order successor, that is 16, and then I will delete this node. So as if you are deleting the key value 15, that is okay, but you are not really deleting the node. You are actually deleting a node that is ultimately in the leaf node. So as we have seen in case of insertion of a binary search tree, that insertion is done always in the leaf node as a leaf node. Here also one thing we can realize, that deletion also happen, you know, physically deletion also happen from the leaf node. In some situation we can directly delete the leaf node. In some other situation, it is not possible to delete the node directly. Rather, we replace the node by a leaf node, and that leaf node we delete. Because you see, in-order successor is a leaf node. So deleting this node will be not a problem for us. Problem will be deleting this. So why I will do this? I will just keep 16 over here. Now you see what will happen if you keep 16. Let's draw it again. So if I draw this one, the newly created node will become what? will be, initially we had 10, 5, 2, and in this side 15 was there. So what will happen? This side remains same, 10, 5, 2. Okay, fine. And in this side, this here we had 15, right? This will be replaced by the in order successor, that is 16. And other part remains same. I just copied it, okay? So other this set of numbers remain same. So ultimately it will become 12, 14, 13. So it's same in the same order, 12, 14, then 13, then 20, 17 in this side. So structurally other part remains same, 20, 17. And obviously here I have 16. I have just copied that. But 16 both it is not a possible, right? That's why what we do? After placing it, after replacing the key value that I want to delete by its in order successor 16, I will vanish this node and also cut this connection somehow. So that means ultimately if you take the in order traversal of this node, what you will see? You will see that it is 2, 5, 10, then obviously 12, 13, 14, then it will be 16, 20, no, not 20, 17, then 20, right? So if you just compare this order with respect to the previous orders, here you see the other order remains same, only 15 has vanished. 2, 5, 10, 12, 13, 14, 16, 17, 20. Here also 2, 5, 10, 12, 13, 14, 16, 17, 20. This is what my point is. That this order should be maintained for the other numbers. Now, naturally question will come that how to find this in order successor. How I am saying this, and so let's try to realize it from the example tree that we have. If I ask you what is in order successor of 10, what will be your answer? It will become 12, right? Because after 10 I have 12. So in order successor of 10 is 12. Now just try to watch the connections between these 10 to 12. I have a just right child and then left. Now if I ask you what is in order successor of 15, you will say 16. What is there? This one. That is right and then many lefts. Now, for example, instead of just writing, I'm just writing as an example. Just forget about suppose this is okay. So suppose this number is not 17. Suppose this number is, suppose it's 19. This is 18, and say I have something 17 and maybe something 17, okay, here. Now if I ask you what is in order successor of 15 in this particular tree, you will say in order successor of 15 is 17, because after 15 if you do a in order traversal, after 15 17 will come. Yes. Now try to make a relation between the how physically they are connected. A right, then multiple lefts, and you see the left, I will stop where I don't have any left child more. So that means if you just for timing, if you forget about this 17, if you just forget about this 17, this part, then you see inner successor of 15 will become 18. In a similar way, if I write say 11 in this side, sorry, and if I ask you inner successor of 10, then you will not say 12, you will say 11. So that means to find inner successor of a node through programming, the job is very simple. You have to go right once, and then you have to go extreme left from this from this particular node. Extreme left means till there is no left child. Whatever last node that we have will become the in-order successor node. So finding in-order successor node is very easy. So just omit these parts. It was not present in our previous tree, and even this was also different here. I had 17 and 16, right? Fine. So that mean if I find, the next situation, that if I find both children, right? This is what I am discussing about, both children's. That means P right not equal to null, as well as P left not equal to null. Then what we have to do? We have to find the in-order successor node first. And how we can do that? We can do easily. I have already seen that. We will start. Suppose I am standing here. This is the node I want to delete. Basically, here we had 15. So here we had a situation is 15. And you are standing here and you realize that this is the node you want to delete, right? This is the key value you want to delete. So this particular part true, right? Because search is now not 4. Here now it is 15. Suppose, assume it is 15, right? So that means when P will point here, naturally you will see that is same value. So I want to delete this, and I will find that both are not null. So it will not come in the case 1. This is for case 1. And now this is for case 2A, rather you can say. So if both are not null, then what you do to find the in-order successor? So obviously you cannot leave this place, because ultimately you have to replace the in-order successor node with, in-order successor node value with this value, and then you have to do further job. So I need one more pointer from where I will start journey, right? So naturally I will start say from, and obviously this is holded by Q that we have seen, because when we are jumping we are storing the parent in Q. So you cannot take Q. For example, take another pointer R. Okay, another pointer R, and I will initialize R as P. I will start from the same node, and what we have seen that we will go right once, then multiple lefts until I find a left child. There is no left child, right? So the program is very easy. I will just blindly write R equal to R right, and then I will continue R r equal to r left until r left is not equal to null, right? You see, I will start r from here. Now when r equal to r right, now r will point here and it will go on continue left till r left not equal to null. So when r will point here, then r left is null. So this loop will break. So when the loop will break, your r is standing in this node, right? So r is no more pointing these nodes. Now what is your job? We have to replace it. Just we have to replace this node value to this node. So I will just blindly write that p data equal to r data. That's all. So what will happen? Let's manage this one. This 15 will be replaced by this value 16. And now what I have to do? I have to vanish this node. I have to vanish this node. But vanishing this node, okay. But not only vanishing. If you want to vanish this node, I have to cut this connection also. And if I want to cut this connection, the left pointer of its parent should become null. Unless if I start, do a journey in the same path, there will be a problem in future. So one thing I forgot to, right now we can realize one more thing I require. That is another pointer which will store the address of R, parent of R, address of the parent of R. So that means here I require one more pointer, not only R equal to P, but also another pointer, say for example S equal to P. Before you jump R equal to R right, it's fine. So when your R is here, then your S is here, fine. And within this loop, before you go R equal to R left, you should store the current R in S. So that when R is pointing here, S is pointing here. Now my job is easy. I don't need to even check whether R is left child or right child. R is surely left child. I am coming for left. There is no concept of right, at least in this loop. So that means after copying this value, I can just write that S left equal to null. Become this particular connection has crossed. Now I can vanish this R, so I can simply write free R. Now this is a general situation actually. What I mean to say that suppose I want to delete, for example, say suppose I want to delete assume this situation is not even present here. Okay, so let's take a situation that I have one value here. Suppose there is a value, suppose 7. If I want to delete 5, then what to do? 5 has both children according to this situation. So if 5 has both children, then 5 has to be replaced by another successor first. And then only you can actually delete the Inora successor node. right? So that means you see, S equal to P. Just a minute, let me check it once. That is S equal to P. If I write this is R, this is S, R right, this is S. S left will become null, which is not true. No, there will be a problem in this situation, because you see what will happen. This is my P right now. I want to delete this. I mean, let's do it. Take another color so that you can understand. So this is my P. Also this is my R. Also this is my S, right? At least with respect to the code. Whatever is P, that is also R, that is also S. Fine. Then R equal to R right happened. So that means R now pointing here. Right. And I can see that R is not there. Fine. Now you see this particular loop, while R left not equal to null. So initially the R left is not equal to null because there is nothing in the left of 7. So what will happen? The loop will break at the same time. I mean at the very beginning without running even once. So when the loop will break, according to the code, P data should be equal to R data, and basically what will happen? P data, that is this one, 5 will be replaced by 7, fine. But problem will happen for this line, because S left equal to null. What is S left? S is pointing still here. Since there is no left child of R 7, that's why R has not changed its position and S has not came here. That means if this S left equal to null is executed, what will happen? This entire path in the left subtree of 5 will get vanished. The line will cut and it will, permanently vanished from the actual, original tree, which is not expected. So before you use this particular line, we must ensure one thing, that at least the loop ran once. If the loop doesn't run even once, then there is no meaning of executing this statement. So that means somehow we can say that here we put an if condition. I mean, if I just write, if I execute this one, I mean, just write down, maybe you can write down something like I equal to 0, and here you will keep on I equal to 1. That means if the loop run once, then I will change, and if the loop actually break at the very beginning, then I will remain 0. And if I remain 0, there no need to execute this particular statement. So that means for this case, I must have a condition that if I is equal 1, then only you can write this statement. If it is not 1, then there is nothing. You don't need to even write. In this particular example, Even if you skip this s left not equal to null, doesn't s left equal to null, doesn't matter, because it has copied and this part will vanish. So that means in that case the right part of this 5 should become actually should become null. So that means in the else part, what we have to do? We have to write s right equal to null. If I equal to 1, then s left equal to null, otherwise s right equal to null, because ultimately loop, since the loop didn't even run once, that means whatever from wherever I have replaced is nothing but in the immediate right side. That we have seen here, you see, is the immediate right. So in that case, instead of writing s left non equal to null, I should write s right equal to null. And that is what we have written. So that means now this particular part of the code become a general code for handling a situation where p and right also not null and q p left also not null, where the p data contain the value that you want to delete. Now let's take case 2, case B. Case B, this one. What is written? The node has only right child. So assume a situation something like 12. 12 don't have any left child, right? If you want to delete 12, what we will do? Is it possible to put 14 in this side? Actually, what we do, we just assume that you want to delete 12 from this set. If you want to delete 12, that means after 10, 13 should come. After 10, 13 should come. How we can do this? We can do the same job that we have seen in case of case A. That from 12 I will find what is innoda successor. I will replace the innoda successor with this 12 and then I will vanish the innoda successor node. You see, if I am correct, then this 13 will be replaced here. So 12, this part will become 13 and I will vanish this entire part. And if you do the inner traversal, you see 2, 5, 10, then naturally 13 will come, then 14 will come, right? And that is required actually, because 12 will not be there. Only this 12 will vanish. So what we have seen from case A and B, basically you don't need to check whether the node has both children. If the node has both children, then also I will apply the technique of this finding another successor and replacing and deleting the another successor node. If I find the node has only right child, then also I will do the same thing. So that means if a node that you want to delete has a right child, then you don't need to think about whether it is case A or case B. So these three cases actually converted to two case problem. This is case 1, this is case 2. So that means I don't need to check this both condition. I have to check only one condition. this condition is no more necessary, because if I check only this condition, then also I will use this approach. If if I attach another condition with this one, then also I will apply this approach. So why I will go for checking p left? But I don't need. So that means if there is a right child, doesn't matter whether the node has left child or something like that, I will continue searching for the inner successor. I will replace that and I will delete the inner successor node, and also I will cut the connection between the parent of the inner successor node and the inner successor node. The very simple, straightforward steps. Now, if the node has only left child, then we have another situation. It's very easy. Now you see a situation something like this: 20. I want to delete, suppose 20. Then instead of 20, who will come? Naturally, 20 is left, because 20 has left child only. There is no right child of 20. Similar situation, assume 14. Or maybe if this particular node is not present, then 5. So that means when I have left child only, that means if P left not equal to null and P right equal to null. You see, because I am considering I will have a left child only. I am not considering there is a right child. If there is a right child, then I will go for previous case. I don't even think about this. That's why this case is specially for only left child. That's why I have written both cases. Because if I don't write this P right part, then what will happen? If P right is equal to null or not equal to null, doesn't matter. If this is not null, it will work. But I should work it when it is not null. At the same time, P right is null. That's why I have to put both conditions. I've given at least. You may not give if you consider this is the last case, because you have to pass this case number 1. This is case number, actually not A, case number A and B, right? If the condition doesn't satisfied for both these cases, then only you can come here. So you can put this in the else part also. So this is case 2 but C. And what we can do? You see, the job is very easy. That I have to just replace this. I have to just delete this part, and instead of that, means what was the parent of 20, the parent of 20 will become the right child or left child of the parent of 20 will have the child of 20. What I mean to say is that there are two possibilities can arise. For example, assume that you want to delete a node, a situation something like 10, maybe say 5, okay, 2 and 1, and you want to delete 5. So what will happen? Your next new form 10, 2, 1, 1. What happened? Difference is that this is my P. I want to delete this node where I am standing. This is my Q, because when I will search, we have already seen that when I will search, Q will store the parent of P. Fine. And this is the P child. Fine. And we have already seen that this condition has to be satisfied. And this condition is satisfying for this case. So what we can do? We can simply say that Q left equal to P left. Because P left means this address. And Q left means this address, means what will happen? Q will now no more point this node. This particular connection will just cross. Rather, now this will point this node directly. So that means we have to write Q left equal to P left. Because obviously P has left child only, so P left. But you see, take another condition, another situation, example, like 10 and 20, then 17, then 16. So suppose I want to delete this 20. So this is my P and this is my definitely Q. Now here you see, obviously this particular case is actually satisfying this condition. P left is not null but P right is null. So somehow obviously 17 should come up. But in this situation, you have to cut this connection. And this should be your new connection. That means to do this, actually you have to say Q right will be equal to P left. Because obviously P left means this node. But in this case Q right. So whether it is Q left or Q right, it depends upon in which side P is there, in which side of Q P is there, right? That means here you have to just check it, that if Q right equal to P, if Q right is equal to P, that means we will write Q right equal to P left. Otherwise, else, that means if Q left is equal P, I mean the first situation, I will write, basically we will write Q left equal to P left. So whatever, I mean either of these two situations can arise in this case. For example, if I want to delete 14, it will become Q right equal to P left. So that 13 will come here. I mean actually this connection has been established. But if I want to delete 20, I'm sorry, say 5, it will become Q left equal to P left. So it depends. Now obviously one thing is left, that I have cut these connections and this particular connection has been established, but you have to delete this node or maybe this node. So that's why we will just, we can write free basically P, so that you can delete this node. So that means in case of a deleting of a particular node of a BST, also we do in this two strategic way. Although there are basically total number of cases is 1, then ABC, total 4 cases, but we can reduce this by, this is case number 1, this is as a whole AB as a case number 2 and only C as case number 3. So in this way, so this is the way actually by which we can delete the set of nodes, a particular node from a binary search tree. So we can stop the deletion procedure of binary search tree over here. Thank you.